Welcome to computing error bounds. So recall, we've had two formulas for computing error bounds. Oops, bounds. We had our trapezoidal rule formula. So the trapezoidal rule error bound. We had that our error was less than or equal to b minus a cubed over 12n squared times m. Again, this is error bounds for our approximation for the definite integral from a to b with f of x dx. So we had our formula, error for trapezoidal rule is less than or equal to b minus a cubed over 12n squared all times m, where m is a bound for the second derivative of f on AB. For our Simpson's rule error bound, we have capital E sub s as less than or equal to b minus a in parentheses to the fifth all over 180 n to the fourth times m. Let me just verify that 180 is correct. Yes. Again, where m is a bound for f to the fourth on AB, closed interval. So our job here is to find error bounds when approximating the definite integral from 0 to 4 of e to the negative x squared dx. First up, using the trapezoidal rule with 8 sub-intervals. So we did this approximation in our example video for the trapezoidal rule. Now we'll see what a bound for the error would be. So here our f of x is e to the negative x squared. Our a is 0, b is 4, and we're working over 8 subintervals, so n is 8. It turns out, note that the second derivative of f is negative 2 plus 4x squared, all in parentheses, whole thing times e to the negative x squared, which is continuous on the closed interval 8, 0, 4. So our error bound formula applies. So essentially what we need at this point is we need an m. So we need an m bounding that second derivative on 0, 4. So we have a few options for this. You can get the most accurate bound you can by using calculus, finding the extrema. You can get a sort of a larger bound, which is fine, by bounding sort of second derivative by another function. Or you can look at the graph. So for this one, we'll go ahead and bound using calculus and find the extrema. For Simpson's rule, we'll use our other options. So we'll go ahead and use calculus to find the extrema. So we have that second derivative of x is equal to negative 2 plus 4x squared times e to the negative x squared. Our derivative of that is 12x minus 8x cubed, all times e to the negative x squared. If we set this equal to 0, sorry, that should have been 12x minus 8x cubed, all times e to the negative x squared. Set this equal to 0, then we have 4x times 3 minus 2x squared has to equal 0. So we get that x is either 0 or the square root of 3/2. And then we'll check at our critical points as well as boundaries. So let's go ahead and check the value of x at x equals 0, square root 3/2. And then our last option is the second boundary, which was 4. I'm going to give myself a little more space. So plugging in, if we wish to find that second derivative at 0, we have the second derivative of f at 0 is just negative 2 plus 4 times 0 squared, all times e to the negative 0 squared. And that is just negative 2. If we plug in the square root of 3/2, we wind up getting 0.8925 ... And if we plug in 4, we wind up getting 6.97 times 10 to the negative 6. So our absolute extrema would be that negative 2. And so we have the absolute value of the second derivative of f is bounded by 2 on the closed interval 0, 4. So we'll go ahead and pick m equal to 2. And we have that our e sub t is less than or equal to, we do b minus a, so 4 minus 0 cubed divided by 12n squared. We had 8 subintervals, so 12 times 8 squared, and then times m times 2. Giving myself just a little more space. We get that e sub t is less than or equal to 0.166 repeating. And so essentially what we have is our approximation. So our approximation in the video, our approximation in section 5.5, part 3 was off by no more than 0.166 repeating. That too is actually the lowest bound we could have chosen for bounding that second derivative of f. You could have picked a larger value instead of 2, and that would simply give us a larger error bound. So we found the smallest possible error bound. Now let's go ahead and find the error bound when we do Simpson's rule with 4 subintervals. So this is what we did in section 5.5, part 5. So again, we have f of x is e to the negative x squared. Our a is 0. Our b is 4. This time around, our n is also 4 instead of 8. It turns out that fourth derivative of f is 12 minus 48x squared plus 16x to the 4th. That whole thing times e to the negative x squared. This is continuous on 0, 4. So we can go ahead and apply our formula. So what we need is we need m, a bound of the fourth derivative of f on 0, 4. So option 1 is to do the direct calculus approach, which we just did in the previous bound calculations. Option 2 is to bound that fourth derivative by another function. So one option is to bound that fourth derivative of f by another function. So in this case, note the e to the negative x squared is trapped between 0 and 1 for x between 0 and 4. And really just for x greater than or equal to 0. Okay, I need to update my screen. Again, e to the negative x squared is trapped between 0 and 1 for x greater than or equal to 0. So what that means then is that our absolute value of the fourth derivative of f, or our absolute value of 12 minus 48x squared plus 16x to the 4th times e to the negative x squared. This absolute value is less than or equal to the absolute value of 12 minus 48x squared plus 16x to the 4th on the closed interval 0, 4. And so one option is to just find the bound of this quartic polynomial instead of finding the bound of the overall function. So if we find the bound on 12 minus 48x squared plus 16x to the 4th on 0, 4, that will serve as a bound on the original function. Another option is to simply graph the function and find the bound visually. Oh, before I do that, so just a quick comment. When you take the approach where you find another function to bound it, you will likely get a much larger bound than necessary. So this approach will likely give you a much larger bound than necessary. again, as mentioned, another option is to graph the fourth derivative of f that we found and find the bound that way. So I'm going to quickly do that graph and just put a picture in the notes. Okay, so here's our graph of the fourth derivative. So as you can see, the highest value is at x equals 0. And at that point, we have f of 0 is 12. The lowest point is somewhere around x equals 1. And that value is higher than -8. And so what we get is that the absolute extrema on 0, 4 is 12. And so we have that the fourth derivative of f of x, absolute value, is less than or equal to 12 on 0, 4. And so we can go ahead and pick m equals 12. Let me update my screen quickly. Putting this all together, we get that the error bound from Simpson's rule is less than or equal to, we do b minus a, so 4 minus 0 raised to the 5th power, divided by 180 times n to the 4th. So 180 times 4 to the 4th times m, so times 12. And plugging this into a calculator, we wind up getting that our error is less than or equal to 0.266 repeating. So in this case, essentially what we get is that our approximation from section 5.5, part 5 is off by at most 0.266 repeating. So this was using 4 parabolas versus 8 trapezoids, what our error bounds are. In reality, these get rather annoying pretty quickly. If you want to go further than this many steps, further than 4 parabolas or 8 trapezoids. And so most of the time, people will use computer programs to do all these calculations for them. But in this way, you can kind of decide, if you know the bound on your function's derivatives, you can decide on how many rectangles or how many trapezoids or how many parabolas are needed to get the best approximation. And I apologize, the Simpson's rule problem we did was actually using only 2 parabolas, using 4 intervals versus 8 intervals, using only 2 parabolas versus 8 trapezoids. So we got relatively close, given that we only used 2 parabolas. All right, That is the end of our numerical integration section.